Hello, good morning. I am not an MIT professor, and I am not going to talk about deep learning for antibody discovery because that person was unable to be here. And by dint, I think we decided it was my 21st bio-IT, not including the Wests and the Europes. And by dint of that sort of long survivorship, the airplane with the bullet holes, I judge best of show and innovative practices, and we have a dinner for the judges after the first day of the conference usually. And we're sitting at the dinner, and Allie got a text and looked a little worried. And she had the good grace to wait until the wine was poured before she said, "So Chris, you have a talk." So I'm filling in. I'm absolutely thrilled to be here. I am not a scientist. I am a technologist. And technology is not why. It's not mission. Technology is not even what. What are you trying to accomplish? I'm your how to do it person. And I think it's really important as technologists that we understand and engage with the mission and what we're trying to accomplish, because anything else is going to be hobby shopping, right? So have we decided that this works to advance slides? Yes. So I'm going to share some real-world systems that I've worked on. I've spent a while building large-scale high-performance computing systems, data storage systems, and eventually organizations. And I am going to try to speak to you like a strategist, where tactics are reacting to change, tactics are close in. For strategy, you have to look at things that are not changing, and they're hard to find these days. But I assure you there are some strategic principles, there are some things that we can rely on as we build systems that are going to last 5, 10, 20 years. So here's some real-world systems. This is my very first high-performance computing environment back in 2002 at the University of Minnesota. And you can see on the kind of right of the picture, those are a bunch of workstations. We called it the Lobos architecture. Lots of boxes on shelves. And you can see in the middle, there's a really early flat panel. And one of the reasons we put the flat panel there was I didn't know a lot about electricity back when I was building this, and CRTs are power hungry, and we kept popping breakers, so we're like, whittle it down. On the far left of the picture, you can't really see them, but we had a couple of FPGA accelerator boards from a company called Time Logic. So field programmable gate array boards are reconfigurable silicon. And what we used them to do was to accelerate BLAST searches, right? And this is gonna be a theme, that there's always differentiated hardware in your system. There's always something that's a little bit weird, that's a little bit edgy, you don't quite know what to do with it. I have lost so many notes from this time. I think we also had some boards from NVIDIA, and we tried to get them to work to accelerate BLAST. But this Time Logic was really the choice at that time. So fast forward a couple of years, and I had joined a little consulting company called BioTeam, and I had the opportunity to work for NASA. This is their Earth Science Technology Office, a data analysis and acquisition center, a DAC, down in Hampton Roads, Virginia. And on the right top, you can see the first petabyte I had the pleasure to help out building. And it occupied 28 cabinets, 2,500 disk drives. The fiber mess that you see down below was a mistake. I would not do it that way again, because all of those fiber optic cables had to be plugged up exactly correctly. This is where one of my themes will be simplicity is best. Simplicity is better than complexity. And complexity is better than chaos, right? Or being complicated. Simple is better than complex. Complex is better than complicated. Those cables, they're complicated. There's going to be mistakes. So as a strategist, as a technologist, we want to make sure that things are comprehensible, that people know how they're supposed to work, why they're supposed to work, that you can see at a glance that things are working right. Also, do you remember that Apple used to sell both enterprise storage and servers? I think we all thought that was going to stick around, and it just did not. So fast forward a little bit further, and this is the New York Genome Center in Manhattan. We built that out from scratch. And now my petabyte fits in half a rack. Things move really, really fast, but there's still about a petabyte of storage that's supporting a diverse community of researchers. There's still a couple thousand cores of commodity compute. There is still some differentiated compute in there still with the GPUs. And what we see in 2012 here is that there's a bit of cloud. And cloud doesn't photograph so well with my cell phone. So I'm going to start using logos. But We, at the Genome Center, the very first thing we built out was a cloud capability. And then what we realized pretty quickly was we didn't have the tooling and the expertise and the DevOps capabilities and the infrastructure as code capabilities. And so we kind of backed into, okay, we'll do hardware again, that's fine. And fast forward a little bit more, and we're at the Broad Institute, where I inherited 2 data centers, about 30 petabytes of storage sort of smeared across 2 data centers. The differentiated hardware in this case was from Cray. And at this point, we had quite a lot of cloud. And we went with Google for reasons of executive alignment. As a technologist, you don't always get to do the bake-off and your favorite thing and the fastest and the cheaper. Sometimes you look and you're like, what is the relationship between these organizations? Where can we have strength on strength from a business perspective? When I started at Broad, we had basically no cloud footprint, and by the time we got to my departure a couple years later, we were 60% production in the cloud. And it turns out that despite what people will tell you, all systems are a little bit hybrid. There is still always a reason to keep a little bit of metal around. There's always a reason to keep the capability to burst somewhere and to become a little bit more hybrid. It takes a decisive click. So then we get to Semaphore, which was a genomic diagnostics company. And this one I really am proud of. This was 99% cloud. We had a couple of legacy infrastructures, but it was a green field, and we got to build new. And what I learned there is that when you build in the cloud, you really have to document things, because there's no wires you can look at. You can't go in and try to kind of back out what was going on. And this worked quite well. And I will share some thoughts on how to architect for mostly cloud versus mostly on-prem. And then we come to this year. And this is a new institute in Cambridge, in Kendall. And we again have about a petabyte of storage. And at this point, it's 2 rack units. It is not most of it. And we have 1,000 cores, which fits in less than half of a rack. And we have, okay, we're going to call them artificial intelligence now. They are still differentiated hardware. And the most important thing for my eye as a strategist, as an architect, is the network. Because I know that most of what's important computationally, data-wise, is not within those 4 walls in Kendall. It's not even in my data center. So what I want is really clear, fast light paths getting me anywhere in the world in less than a second. Which leads me to my first of 5 points, power cooling and information transfer. With the New York Genome Center, we worked for the data center with a man named Dave Saby of Saby Data Centers. He is based out of Seattle, and he had the observation early on that electricity is expensive, cooling's a pain, and light is really, really fast. So this guy put his data centers next to the hydroelectric dams, the Hoover-era hydroelectric dams in the middle of Washington State, where he could get power at 2.5 cents on the kilowatt hour, and where it was pretty easy to cool. And he laid in fiber optic cable to Seattle. And if you've heard of a Seattle company, they are hosted at Saby. It was a good decision. And power is not really a mystery, right? We've had Ohm's law for a couple of hundred years. Watts and amps and volts are related to each other. Watts, by the water metaphor, is the amount of power. This is why you get a bill for watts. Amps are the pipe capacity, the capacity of the infrastructure. And voltage is the pressure. I've been using this consistently for more than 2 decades in building out these systems, and it always seems to come back to bite me. I've heard about all of these, off-site and cloud and all of this. I always seem to have to know this formula. And it's really easy to remember that voltage is the pressure. When we were building at the Genome Center, the building process. Has anybody in the room been through a facility build at scale, a really big one? The facility construction meeting is a fantastic artifact. It's an amazing thing. And the owner's representative for the New York Genome Center was this consummate New Yorker, incredibly skilled, incredibly forceful, crass, the kind of guy who would cuss you out in an email. And one day he was haranguing the plumbing team, and he said, "Have you installed the pressure reducers in the basement?" And they had not. And he said, "Well, guys," profanity ensued, "if we don't get that street water pressure reduced, you're going to blow the urinals off the walls." That's what happens if you have too much voltage. It's dangerous. It damages stuff. Also, high voltage is how you get efficient power distribution. So the choice of where you put your high voltage, where you reduce it, where you put your computers. This is solvable, and it is not solved in an arbitrary way, but it's not complicated. This is Fourier's law. It governs heat transfer, because once you get power into a computer, you got to get the heat away. Computers are hideously inefficient machines. They're just little heaters, right? And it's the same formula if you kind of squint. You can see there's the amount of energy that moved, there's the efficiency of the moving, and there's the gradient, the pressure. And the really important thing to remember here is that the thermal conductivity, the efficiency of moving heat between objects, is incredibly less efficient in gas than it is in liquid. About 25 times less efficient to try to move heat with air than with water. And it's about 10,000 times less efficient to try to move heat with air rather than metal. Easy way to remember this, you put your hand close to the stove, no problem. You touch the stove, you get burned. And this is why when we want to cool a computer, as we're putting more and more power through it, we rapidly think about liquid cooling, right? And we're seeing all of these liquid-cooled systems for the NVIDIA boards, for the AI boards. One of the racks that I showed you, the most recent one, can handle about 17 kilovolt amps. And the racks that they are building for NVIDIA devices are on the order of 120 kilovolt amps. And the engineering required for that is pretty intense. Another short story, the Cray 2. Does anybody remember the Cray? I had the privilege of working with some crayons back in Minnesota. That was what they called themselves. And I heard the story of the Cray 2, the first fluid-immersed supercomputer, and how they would tune those machines. And it was simple. Again, like simplicity is better than complexity. You take a board, you put it in the non-conductive fluid, the floor inert, they called it, and you turn up the fluid velocity until the components peel. Then you get another board. You turn it up to just below that, and then you turn up the clock speed until you see bubbles. That's where you lose your cooling efficiency. You turn it down just a little bit, and now that machine is running as fast as it can. Doesn't have to be complicated. Everybody in the room can see that that is the fastest you can go with that particular setup. And finally, here's Shannon-Hartley theorem. This is channel capacity. This is how much information you can get through a pipe. And if you really kind of squint your eyes, it's kind of sort of the same. It's not exactly the same, but it's close. And this is because human minds all kind of think we have small minds, right? And so you have to kind of compact it into ideas you can understand. And the important output of this is that we are nowhere near the capacity of single-mode fiber from a theoretical perspective. Our lasers are not quite fast enough. Our clock speeds don't go quite fast enough. But if you have good, clean fiber, as my friend Dave Saby observed, you can just keep swapping in new optics and keep up with technology. So as a technologist then, as a strategist, as a person who's asked, where do I put the computers, what do I invest in? Good fiber. Well, I think it's actually on the summary slide. You put your computing infrastructure next to cheap renewable power, someplace where it's straightforward to cool it, and it's okay, you can get the HVAC engineers in, and close to high-quality fiber. And it's probably not your basement. And I know that at the NVIDIA conference, we were told that the data center is dead. And I just don't think that these things changed just because boards got denser and people are very excited about AI. I don't think that it is sensible to try to bring interstate transmission voltages into offices and warehouses. I think that would be a mistake, and I think that people will figure that out. I think that doing the complex HVAC engineering to plumb up liquid-cooled systems is hard, and people will specialize in it. So I'm pretty bullish on data centers. We may not own them, they may be farther away, because 80 milliseconds to get coast to coast over the commercial internet, most of us don't need latencies faster than that. Even gamers, even those of us who play quick twitch games are playing over the internet, and it's fine. All right, so next up, a little bit of science. And as I mentioned, I'm not a scientist by training, so I'm not as deep in this. And at risk, I will say that the underlying mechanisms of biology have been pretty stable for millions of years. It's our models of them that change rapidly. And that's a distinction that very frequently gets lost in casual conversation, especially if people have read popular press books and they think they understand that DNA is the programming language of life or something. That's a model. And the molecules are pretty constant. So here's something that I skimmed through my slides from the past bunch of bio-IT worlds. Human genome hasn't changed size much in 300,000, maybe 3 million years. We're diploid, we got 23 pairs of chromosomes, about 3.2 billion unique loci. I've been paid to answer this question so many times, I'm giving it away for free. Please never pay for this again. About 2 bits for a base call, about 8 bits for a quality score, 10 bits per base pair. 3.2 billion times the depth of sequencing is the approximate number of bits you need on disk to store it. Is anybody from Petagene here? Okay, Petagene sells a really good compression software that will beat this. But in terms of the logical size of a human genome at 30x, it's been about 120 gigs for my entire career. What has changed is that used to be way more than I had on my laptop. And now my laptop contains a 2 terabyte drive, so it's not as hard anymore, right? This one. So what does science do? Science does more. Science pushes us as technologists to see how far we can go, but the point should always be the science. TCGA, the Cancer Genome Atlas, defined these levels of data. And level 1 is what came off the instrument. You did an experiment in a lab, and you got reads, you got gel images, something. The important thing about level 1 data is it is immutable. You can keep that forever. This guides your data strategy, right? At level 2, we normalize. Maybe we base quality recalibrate. Maybe we do quantifications and we turn those gel images, we put numbers next to them. Still immutable, statement of fact. That was what the experiment said. At level 3, we inform it with a model. We turn it into variant calls. We didn't do an experiment to find a variant. We got a bunch of reads. We didn't do an experiment that told us a pathway is upregulated. We measured the presence of peptides. And that works really well if you are in conversation with another domain expert, but people get confused as soon as you have a popular press reading, a different kind of expert. God help you if you're overloading language like we do. Mathematicians think vectors are something very different from biologists, something very different from epidemiologists. And if we casually use language and we're not really careful with our models, it can be very confusing. Imagine if you just had a machine mashing that together. You would get some very silly answers from that machine. And then at level 4, we interpret. And we all know about interpretation. You know, what I said was this, but what did it mean? What was he getting at? So as a data strategy, so there's one more slide here. Parsimony still holds. If what you want to do is figure out whether a mouse is going to be dead, yellow, or white, you could ask an LLM. I'm sure somebody's going to go ask ChatGPT right now. I didn't. I don't care. It might be right. You could do a GWAS, a genome-wide association study, and you would get, I forget how big the mouse genome is, but you would get billions of floating point numbers, and you'd have no idea what it meant. It would bring up more questions than it solved. And or you could use something that they came up with more than 100 years ago, a Punnett square, and you could get the right answer every time. Simple answers. It doesn't have to be complex. There's a lovely review in Eye by Mackey a couple years ago. What color are your eyes? How many pages do you think that paper is? How many different ways could you interrogate the question of what color are your eyes and why are they that color? And you have to ask, well, why are you asking? Is this an elementary school student? Is it somebody who's working on a medicine for eyes? Is it somebody who's looking at inherited disease? You know, there are lots and lots of different ways to answer a question, and you have to be cognizant of the why. You have to know why they're asking the question. What are we trying to accomplish? And then I'll tell you how we do it. So, data guidance, store primary data forever, be prepared for a lot of multiple versions of level 3 and above. And be cognizant of models, like simple pictures are best. All right, moving on to business, which I'm even less experienced with. I have learned about business because I must as I have gotten older and my technical skills have gotten more rusty. The joke is you can't have any of these. But fast and cheap and good is your traditional pick one. As an organization, there's no right answer. It's context dependent. And in biotech, we start off in fast. Early discovery. You've got a bit of seed funding, you've got to prove out some IP, you've got to demonstrate some science, right? This is where you hire consultants, the very best consultants you can get. And there's more of you in the room. You use the cloud all the time. You use value-add markup platforms on the cloud because, God, why would you do anything else? There is no excuse at the beginning to wait for a server to be delivered, to wait for somebody to re-implement a GWAS, to wait for somebody to make up a new data format. No excuse at all, because you're going to die if you don't prove your IP before you run out of money. If you are fortunate enough to get towards the clinic, you start to move towards good. At this point, we start hearing things like quality and reproducibility and governance and compliance, and you start bringing in people who know about GDPR and Section 11. You didn't need those when you were going fast, when fast was the only thing that was important. But wow, you need them to get through the valley of death. This is where we see companies internalize some of their core functions. You start to see, rather than all those consultants, we got to bring somebody in who owns quality, who really owns information security. You start applying for cyber insurance. You got to put a name on the line, right? And then finally, if you are so fortunate, you get to cheap. You go for profit. You are in a business now, perhaps you're acquired, perhaps you just have lines of business that you're out selling. People start asking about margin. And then, oh my God, why are they using this cloud thing? It is so blindingly expensive. What were they thinking? Where are we going to put the computers? Don't we have a data center? Don't they know that if you are renting from Amazon, the breakpoint is about 10% utilization before you can do most commodity things yourself cheaper, if you're at scale, right? That's the same point where companies will start hiring cooks and building a kitchen rather than catering every single meeting. That was the single most impactful cost savings at the Broad. When I was there, there was no regulation around catering meetings when we started, and the chief operating officer, Samantha Singer, amazing boss, said, hey, what if we negotiated our catering? And we said, there's only 3 places you can get it from, and she saved millions per year just with that decision. That's not a fast strategy. That's a save money for science strategy. And I would say it is very, very common when I ask this question of my clients that an executive leader will say, well, yes. The answer to fast, cheap, good, yes. It doesn't help. And it's unfair to the team to keep our actual strategic status opaque and force us to guess. So if you are in an executive role, I encourage you to answer that, to really provide an answer. Would you like it first? Would you like it to be absolutely ironclad in terms of quality, or are you going to talk about margin? So technologists, I know that we love our technology, but you got to know about the business priorities. You've got to align with them. Nobody cares about the technology. And I say that here in the age of AI hype, but really in terms of delivering on business objectives, unless you are NVIDIA, nobody cares about the technology. Strategists, your translators. If you have director or senior director or V in front of your title, you got to translate. And you've got to plan for success for the time when fast is not the only thing, when you might actually be evaluated in terms of cost of goods sold, when somebody might say, can we move that to a cheaper geography? And if you are unable to answer that question, you have made a strategic mistake. Then executives, be clear, be honest with us. It really does help. All right, onward to technology. This changes like you wouldn't believe. All of those prior statements have been pretty constant as long as I've been watching. But wow, technology goes fast. 2007, Amazon launches EC2 and S3. I wrote a Perl script. It was what I did in reaction to change at that time. So I literally replaced myself with a Perl script. I spun up and this script was weird because the first thing it did was make infrastructure that it needed to do its bottom half, right? Spun up an instance, put a database on it, put a web server on it, screen scrape a bunch of other websites, put that in the database, and look at my summary. And I would rerun that from time to time to answer questions. How many people did that? Yes, one, two, several of us. This is what we did, right? And over time, cloud technology, and that was cloud, right? But that was a very much forklift, lift and shift cloud. Right? Over time, we got to using things in a more cloud-native way. The server and the standalone database go away. Me pushing the button goes away. The screen scraping goes away as more institutions offer seamless API into their data. Thank you, Snowflake. Perl went away. And much of the HTML intermediation went away. And then we were down to just, I need an updated view of what all of these data repositories say about something that was of interest to me. That was what I was trying to accomplish. This was my whiteboard at the Broad in 2013 when I was trying to really understand our cloud strategy. Because it seemed like nothing technical that I could do would scratch the itch of having a cloud strategy. There wasn't a, what do you need to go faster? What do you need to be cheaper? You know, and we needed to align with this technology revolution. It can be very frustrating for a technologist to be told again and again, AI, and say, what is it? And there's a reaction that is very common, which is to say, well, how many millions of dollars would you like me to spend on that to scratch this itch? I see a lot of that. I see a lot of institutions investing because they're sure there's something there. And there are people in the middle of those organizations whose whiteboards look like this. I'm sure there are. Perhaps a slide advance, please. Thank you. So this is a quote from a book that was written in the 1600s on Chinese brush painting. It's one of the classics if you're into such things. And the quote is, "To be without method is deplorable, but to depend entirely on method is worse." And so I said back in 2013, to be without cloud is deplorable, but to depend entirely on cloud is worse. And now to be without AI is deplorable, but to depend entirely on AI is worse because it's just a how. It's just, how am I going to do this? And it begs the question of, what am I trying to do? Well, in brush painting, I'm trying to make somebody else feel what I felt by way of ink on paper. You know, and with technology, we're trying to improve human health by making more effective therapies, right? The technology comes third. We had this term that started showing up a few years back, cloud hangover, as organizations realized that they had turned themselves into a cul-de-sac and they were spending way more money than they had to, and they had lost agility with their agility play at scale. It was mostly a realization, I think, that rental economics hold even as technology changes. I think we're going to have an AI hangover. I think the AI hangover will be when we realize that domain expertise matters. And I think that we are going to retrench back and realize that firing our experts and firing our junior people was a terrible, terrible mistake. I think that will be a hangover that is lasting. And finally, I want to talk a little bit about people. When I was at the University of Michigan, although those many years ago, I took a literature class, and the professor's first day, he said, people have not changed in thousands of years. This is why the classics still resonate. When I was working for Samantha Singer at the Broad, I asked her if these leadership techniques she used were portable, if they were specific to just that institution. She said, any group of people, this is how they work. Everybody had a first day. There are always junior people, and it is on us senior people to coach and develop them. This quote is Hyman Rickover. He built the nuclear navy, and he says, by working 24/7, you could possibly get 3 shifts out of this one human body. And if you want to multiply yourself more than 3 times, you must train, you must develop a bench, you must learn to manage, you must delegate. Those people on their first day know a lot about new tech. They know way more than we do, and they've never built anything big. The way you develop a junior person into a senior person is through the practice of the largest survivable failure, and it is terrifying. But I assure you, every single one of you was given a task by your boss that they could have done faster. And they waited. And they sat on their hands as you got it wrong. And then eventually you knew how to do that thing, and they didn't have to ask after it ever again. We have to keep doing that for our junior people. We cannot just use the technology of the day to summarize or read or propose an algorithm or propose a solution. We have to keep developing our junior people. It is the only way we get experts. Investors are great, but they're not scientists, and they're not technologists. They have a different job. They come to healthcare and life sciences because we are a good bet. We are still a good bet. And it is on us who work in this field to tell them what is easy and hard, what is ethical and what is atrocity, what is possible right now, what is difficult but maybe, and what just isn't going to work. They don't know. They know finance. They have access to incredible resources. We have to help them. It is on us to push back, and it's hard, but this was an article that came up recently. It's the 30 under 30 pipeline to prison. These are very young, early career people who got bad advice. Nobody shaped them. Nobody said, hey, the tech isn't working. The very nerdiest book that I own is Information Risk Concealment and Man-Made Disaster. Every single time, whether it was the Challenger, the dam bursting, 3 Mile Island, there were technologists screaming bloody murder, but they didn't get through to leadership. And finally, people matter. Human organizations are machines that we build. They are systems. And the way we build them under capitalism is pretty simple. They accumulate resource and they grow without limit. It's like a cancer. If we want different outcomes that actually make things better for people, we need to put those requirements in as design. And we can do this. We actually know how to do it. And it's on us to do so. It won't happen by accident, but it is not impossible, and we should push for it. Thank you so much for listening.